As you progress in your flying, you will probably be exposed to more sophisticated aircraft, and along with these sophisticated aircraft come advanced systems. For example, high-performance aircraft may be equipped with fuel injection systems, turbochargers, constant speed propellers, advanced environmental control systems, de-icing or anti-icing systems, and retractable landing gear. In this presentation, we'll look at these systems in detail and provide you with a basic understanding of each one. Since the specific operating procedures for each system vary from one manufacturer to another, you should always consult the pilot's operating handbook or aircraft flight manual prior to operating any unfamiliar system. In an effort to gain the maximum amount of power from small lightweight aircraft engines, manufacturers have devoted a great deal of engineering research to advanced fuel induction systems. One of the most successful of these is fuel injection. Unlike a carburetor which mixes fuel and air prior to reaching the intake manifold, a fuel injection system injects fuel into the intake port, where it is mixed with air just prior to entering the cylinder. This allows for an even distribution of fuel to the cylinders and a more uniform mixing of the fuel and air. Let's quickly look at the components of a typical fuel injection system. The first component that we'll look at is the auxiliary or boost pump, which is usually an electric pump and serves several purposes. Its primary function is to pressurize the injection system prior to engine start. This forces fuel through the lines. The auxiliary pump also maintains fuel pressure in the event the engine-driven pump fails. The next component is the engine-driven fuel pump. Once the engine is started, this pump pressurizes the system by taking fuel from the tanks and sending it to the fuel injector unit. In some systems, the fuel pump supplies more fuel than the injector unit needs. In this case, the excess fuel is routed back to the tank through a return line. In other systems, the fuel is strictly metered and no return line is required. After the fuel is pressurized by the fuel pump, it moves into the fuel injector unit. Here, valves meter the fuel according to the mixture setting and the flow of air into the engine. The metered fuel is then sent to the fuel flow divider, or fuel manifold, which is located on the top of the engine. It's designed to divide the fuel evenly between each of the fuel injection nozzles. Within the divider, there is a set of valves that automatically shuts off the flow of fuel to the engine when the mixture is placed in the idle cutoff position. After the metered fuel leaves the flow divider, it's injected into the engine through the injector nozzles located on each cylinder head. At this point, the fuel is mixed with the air in the induction manifold just outside the intake valves and combustion chamber. A fuel flow indicator, calibrated in pounds or gallons per hour, is connected to the outlet of the flow divider. It measures the pressure being applied to the discharge nozzles. Now that you're familiar with the basic components of a fuel injection system, let's look at some of the advantages fuel injection has over carburation. As mentioned earlier, one advantage of fuel injection is the even distribution of fuel to each cylinder. Let's look at why this is beneficial. On a conventional carburetor system, the metering and vaporization takes place at the beginning of the induction system. Notice how the center cylinder is closer to the carburetor than the cylinders at each end. This results in an uneven distribution of the fuel-air mixture. The ideal solution for this would be to have a carburetor at each cylinder. This is what a fuel injection system does. The injection nozzle acts just like a little carburetor, delivering equal amounts of fuel to all cylinders. This allows for a smoother running engine with more horsepower for the same amount of fuel. In addition, the engine will operate at lower temperatures. This decreases the chance of experiencing detonation or pre-ignition and increases engine life and reliability. Another advantage of fuel injection is that it is not susceptible to carburetor icing. Float-type carburetors are highly susceptible to icing due to where vaporization occurs. As intake air passes through the venturi, it cools. Further cooling occurs during the vaporization process. This drop in temperature can cause moisture to freeze and adhere to the internal parts of the carburetor. In a fuel injection system, there is no significant temperature drop across the throttle valve, so icing is unlikely. In addition, the fuel is vaporized at the cylinder head, where increased temperatures make icing virtually impossible. One place where ice can accumulate in a fuel injection system is on the air intake. If this happens, all air could be cut off to the engine, causing it to quit. To prevent this from happening, some induction systems have an alternate air door. When opened, air from inside the cowling is taken into the induction system. Although this allows the engine to keep running, the reduced airflow and increased temperature affects the amount of power the engine can produce, much like the effect carburetor heat has on a carbureted engine. Although it may sound like fuel injection is the perfect system, it does have some drawbacks, the most significant being the increased possibility of vapor lock. Vapor lock occurs when vaporized fuel blocks the flow of liquid fuel to the fuel injection system. The reason fuel injection systems are more likely to experience vapor lock is because there are more fuel lines in close proximity to the engine and the heat it produces. If temperatures are hot enough, the fuel inside the lines vaporizes, resulting in low fuel pressure or engine failure due to fuel starvation. Fuel-injected airplanes that are flown frequently with only short stops between flights are highly susceptible to vapor lock. This is because some of the heat given off by the engine is absorbed by the fuel lines, causing the fuel to vaporize. Vapor lock can usually be remedied by turning on the auxiliary fuel pump and forcing cooler fuel through the system. The last topic we'll discuss is starting procedures. Although the starting procedures vary between manufacturers of fuel-injected engines, all of them have one thing in common. That is, if the engine is cool to the touch or is being started for the first flight of the day, the system will have to be primed. This is accomplished with the auxiliary fuel pump. With the throttle and mixture set according to the POH, turn on the electric fuel pump and monitor the fuel flow indicator. When a sufficient fuel flow rate is noted, continue with the specified starting procedures. A common area of difficulty with fuel injection is starting a hot engine. As mentioned earlier, hot engines cause fuel in the fuel lines to vaporize. Again, the auxiliary fuel pump is used to purge the system of the vapor lock. When doing this, you want to make sure you follow the manufacturer's procedures to reduce the chance of flooding the engine and possibly starting a fire.
Another aircraft system that helps increase performance is turbocharging. Let's take a look at how turbocharging works and discuss some of the unique characteristics of operating an aircraft that is equipped with a turbocharging system. As you know, when you climb, the ambient air pressure decreases approximately 1 inch of mercury for every 1,000 feet. What this means is that there is less air available for combustion at higher altitudes. Because of this, normally aspirated engines are not able to produce maximum manifold pressure with an increase in altitude. In order for a reciprocating engine to overcome this problem, turbochargers were installed as a means of getting more air into the engine. With a turbocharger, intake air is compressed before it enters the combustion chamber. This allows the engine to obtain higher manifold pressures, which equate to increased engine output. To better understand how a turbocharger works, let's take a brief look at the components of a typical system. There are 3 components that are common to all turbocharging systems. They are the compressor, the turbine, and the wastegate. As air enters the intake, it passes through a compressor where it is compressed by the centrifugal force created by the impeller blades. The compressed air is then routed from the ring surrounding the impeller through the throttle body to the cylinder. The compressor is driven by a turbine which is propelled by the engine's exhaust. If all of the exhaust from the engine were allowed to pass through the turbine at low altitudes, the compressor would produce excessive manifold pressure and high operating temperatures. To alleviate this possibility, a wastegate is added to the system to control the amount of exhaust gas that is routed through the turbine. When the wastegate is open, most of the exhaust bypasses the turbine. In this situation, the engine operates much like a normally aspirated engine. When the wastegate is closed, all of the exhaust gas is used to spin the turbine. In this case, the maximum amount of compressed air is being delivered to the manifold. In some turbocharged engines, the wastegate is controlled by a pressure-sensing controller mechanism and a wastegate actuator. Once the manifold pressure is set on this type of system, the wastegate position adjusts automatically to maintain the desired power output. On less complex systems, the position of the wastegate is regulated by throttle movement. When the throttle is moved forward, the wastegate moves to the closed position. When operating this type of system, you must give close attention to throttle operations, since excessive manifold pressures can be produced at low altitudes. For specific operating procedures on the turbocharging system you're using, consult the Pilot's Operating Handbook or Aircraft Flight Manual. An area you need to be familiar with before operating a turbocharged engine is critical altitude. This occurs when the wastegate is completely closed and the turbine is spinning at its highest speed. Once the critical altitude is reached, manifold pressure will decrease with an increase in altitude, just like a normally aspirated engine. Another concern for turbocharged engines is the shutdown procedure. After a flight, the turbine may still be spinning at several thousand RPM. When you shut the engine down, the oil supply to the turbine is cut off. Therefore, before shutting the engine down, allow the turbine a chance to spool down with oil being supplied to it by idling the engine for the time specified by the manufacturer. When you get into a high-performance aircraft for the first time, one of the differences you'll probably notice is the propeller pitch control next to the throttle. As you will soon learn, this control is used to vary the propeller blade angle to gain additional performance and efficiency from small, lightweight aircraft engines. Before we get into the mechanics of constant speed propellers, let's quickly examine why they are more efficient than fixed-pitch propellers. Thrust is a product of engine horsepower and propeller efficiency. If a propeller could operate at 100% efficiency, all of the engine's power would be converted into thrust. However, no propeller can attain 100% efficiency. Moreover, a fixed-pitch propeller produces its maximum thrust only at a specific RPM and airspeed. For example, a propeller with a low blade angle is very efficient at low air speeds, such as during takeoffs and landings, but its efficiency decreases rapidly as speed increases. Whereas a propeller with a high blade angle is more efficient at cruise speed. Fixed-pitch propellers can be designed either with low blade angles to produce optimum takeoff and climb performance, with high blade angles for optimum cruise performance and fuel economy, or as a compromise between the two. On aircraft equipped with constant speed propellers, the propeller can be adjusted to maintain the optimum pitch angle. Thus, constant speed propellers can maintain a high level of efficiency over a wide range of airspeeds. Before we get into the operational considerations of constant speed propellers, let's briefly examine the components of a typical system. These include the throttle, the propeller, or prop control, the governor, and the propeller itself. Unlike the throttle, which controls RPM on an aircraft with a fixed-pitch propeller, the throttle on an aircraft with a constant-speed propeller controls manifold pressure. The manifold pressure gauge is usually located near the tachometer and is sometimes combined with the fuel flow indicator. Since the amount of power that an engine produces is directly related to the fuel airflow, manifold pressure increases as you move the throttle forward and decreases as you move it back. The prop control is used to set the propeller RPM by changing the pitch of the propeller. When the prop control is full forward, the propeller blades are at their lowest pitch angle and produce the highest RPM. When the prop control is pulled aft, the propeller blades move to a higher pitch, resulting in a lower RPM. The prop control is connected to a governor, which is located on the front of the engine. The basic governor contains an oil pump, a valve, flyweights, and a spring. The governor maintains a specific RPM by directing oil to or releasing oil from the propeller hub to adjust the blade angle. The propeller hub houses the propeller blades, which rotate on a set of bearings, and a piston, which when pushed by oil, causes the blades to rotate to a higher pitch. When oil is released from the hub, aerodynamic forces acting on the blades of the propeller will twist the blades to a low pitch. Now that you're familiar with the components of a constant speed propeller, let's take a moment to examine how these components work to control a propeller's pitch. When you set the prop control, you're actually setting the spring tension in the governor to maintain a desired RPM. With the tension set, the system remains in a state of equilibrium until the aircraft accelerates or decelerates. When your airspeed increases, the propeller RPM also increases, which in turn increases the centrifugal force acting on the flyweights. This causes them to tilt outward, putting more tension on the spring and raising the valve. With the valve in this position, boosted oil is routed to the propeller hub. Once the oil reaches the propeller hub, it pushes the hydraulic piston rearward and increases the blade angle. This reduces RPM until the centrifugal force on the flyweights decreases and allows the valve to return to the neutral position. Conversely, when your airspeed decreases, propeller RPM decreases. This causes the flyweights to tilt inward. The decreased tension on the spring lowers the valve and allows oil to drain from the propeller hub. As this happens, aerodynamic forces acting on the propeller blades decrease the blade angle, resulting in an increase in RPM. With this type of system, a loss of oil pressure or governor failure results in the propeller blades returning to low pitch. Most multi-engine aircraft have what is known as featherable constant-speed propellers, which allow the pilot to rotate the propeller blades so they are nearly aligned with the relative wind. This reduces drag should an engine fail. In this system, oil pressure is used in conjunction with aerodynamic forces to decrease the pitch of the propeller blades and a set of counterweights to increase the pitch. When the propeller is spinning, centrifugal force pulls the counterweights toward the propeller's plane of rotation. When oil pressure is removed, the counterweights overcome the aerodynamic forces on the propeller and rotate the blades to their feathered position. Now let's take a look at some operational considerations when using a constant speed propeller. Although engine designs vary, as a rule, you should avoid excessively high manifold pressures with low RPM settings, because high cylinder pressures can damage the engine. One way to avoid this is to always keep the prop control in the high RPM or full forward position during ground operations, takeoffs, and landings. Another way to keep from damaging the engine is to follow some basic procedures when decreasing and increasing engine power. For example, when reducing power, first decrease the manifold pressure with the throttle. Then decrease the RPMs with the propeller pitch control. It's important to note that as propeller RPM decreases, manifold pressure increases slightly. Therefore, to avoid excessive manifold pressure for a given RPM, it's best to initially reduce the manifold pressure below what is desired. Then, after the RPM is set, adjust the throttle to the desired setting. When increasing power on an aircraft with a constant speed propeller, begin by increasing the RPM, then advance the throttle. Constant speed propellers can give you better climb rates, higher cruising speeds, and extended endurance due to reduced fuel consumption. However, since the combination of manifold pressure and RPM setting needed to achieve a specific performance varies from one aircraft to another, always consult the pilot's operating handbook for the recommended power settings. So far, we have looked at how fuel injection, turbocharging, and constant speed propellers can increase engine performance. But as you extract more from the engine, it becomes more and more important that we observe the operating limitations and follow the procedures established for the aircraft by the manufacturer.